announce a talk on Russian optimization seminar, Polish Russian seminar. This is George Lan from Georgia Institute of Technology. I asked Arkady Semyonovich Nemirovsky to advise me someone who make a talk on first order methods, and Arkady Nemirovsky advised to invite George Lan as one of the maybe best specialists for first order methods, accelerated algorithms, and so it's our pleasure to have a talk of George Lan, the title Projection-Free Methods and their Application. George, please start.
Well, thank you very much, Alex, for inviting me to give a talk. It's really my pleasure, my great pleasure to give a talk in Boris Polya's Russian seminar on optimization. So, you know, many of my research had roots in Russian research community, right? So I feel privileged to give a talk here. So today I'm going to talk about projection-free methods. I'm going to start with the basic and the classical conditional gradient methods, and then present some of our recent research results in this area. So, so I'm going to start with a few applications that inspire us to use projection-free method, including novelty detection, matrix completion, and some applications in healthcare industry, namely the intensity modulated radiation therapy problem. And then I'm going to see how simple conditional gradient method can be used to address some of the challenges arising from these applications. And then I'm going to present some new algorithms for solving, you know, problems with more complicated constraints, which cannot be handled by classic conditional gradient method. So which include the constraint-extrapolated conditional gradient, and the constraint-extrapolated and dual-regularized conditional gradient. And then we are going to apply these new methods for solving the IMRT problem. I'll start with the background of our research. So, you know, during the past 10 years or 15 years or so, we have seen an increasing interest in applying optimization in many different areas, including statistics. So I think that was, I graduated about 10 to 11 years ago. At that time, so we were very excited that, okay, so now optimization, especially continuous optimization, can be used in solving many statistical problems. Then a few years later, I think that was about the time when I was assistant professor in Florida. So we realized many of our methods, including, you know, the stochastic approximation algorithms that we developed when I was a student with Arkady Nemirovsky and Juditsky and Alex Shapiro, were used in machine learning. And then we realized there is a huge demand in machine learning area for optimization algorithms. And then you see the field is getting involved very quickly. During the last 3 or 4 years, I think artificial intelligence now becomes, again, a buzzword, and a lot of problems in that area has been formulated as optimization problems. So no matter how those buzzword changes over time, optimization seems to be, you know, a crucial methodology for solving those problems, for analyzing those problems. So statistics, machine learning, artificial intelligence, they still belong to methodological area, and optimization has been applied for solving, you know, many real-world problems. For example, in engineering design, when we were students 10, 15 years ago, we were excited about, like robust optimization applied to trust topology design, structure design, and the optimization always play a significant role in finance, in portfolio optimization, asset allocation, and recently, more and more interest are paid, or attention has been paid to healthcare industry. I believe the trend is going to continue, as you can see, especially due to this, COVID-19 and this kind of thing. So today I'm also going to talk about some applications in healthcare industry to illustrate this application to effectively solve our algorithm. So as optimization becomes more and more, accepted in applications, so we have seen a lot of challenges that probably new to us. Okay, so one challenge is high dimensionality in statistics, machine learning. So the optimization problems can easily have millions of variables or more. The second challenge comes from the solution sparsity. So we often require the solutions have like long zeros. The number of long zeros is small, the rank is small, and those sparsity have either statistical or physical meaning, as we will see a little bit later. The third one, I cannot say it's challenging, but it's some new characteristic for the design of optimization algorithms. So right now, we don't need to seek very highly accurate solution. Low or moderate accurate solution is acceptable. I will illustrate this in applications. Lastly, practitioners, they don't want to just call a black box to solve the problem. They would like to see inside the solution methods so that they can implement those algorithms. They can tune some parameters for the algorithms to fit their need. So that requires us to design simple optimization algorithms rather very complicated ones. Those are a few challenges that I can see as we can illustrate from the following applications. So the first application is about novelty detection. So in this problem, we want to find the boundary between the inlier and outlier data points that we have connected, as you can see from this this picture. Okay. From this picture. So the inside the circle are inlier data points, outside the circle might be outliers. So the problem can be formulated easily as the minimal enclosing ball problem. So basically we want to determine the center C and the radius R of the ball so that this ball covers the inlier data points. So this is problem with, you can formulate this as a problem minimizing R so that, the norm square between xi is a data point to the center C of the ball, less than equal to R, okay? So this problem can be write down, so we can write the dual of this problem, okay? The dual of this novelty detection problem is actually a quadratic optimization over a simplex constraint. So as you can see, the objective G alpha is a quadratic function, and the constraint is, okay, summation of alpha equal to 1, alpha is non-negative. So it's a standard simplex. How do you derive it? You may have many different ways to derive it. One of the simplest ways would be to write the Lagrange function and set the partial derivatives equal to 0. And then use it to simplify the Lagrange dual. So then you will find this problem is a standard quadratic optimization problem over simplex. So what is the challenging? What are the challenges for solving this problem? So first of all, the problem is of high dimension. So if you have a connection of 10 to 6 or more data points, then you will have 10 to 6 or more dual variables. Secondly, the solution for the dual problem is very sparse. Okay, many data points will be inside the ball. Only very few data points will be on the boundary of the ball. So that means for those points inside the ball, the constraint in the primal problem is inactive. That means the corresponding dual variables r of I will be 0. So you are going to have a very small number of non-zero solutions, non-zero elements in the optimal dual solution. So certainly, we don't need to solve this problem to high accuracy because the data points that we connected have some inherent uncertainty. So you don't have to solve this problem to like 10 to minus 5 or 6 or even more. So you only need to solve this problem with moderate or low accuracy. Okay, this is our first example. The second example is also a popular one. It's called recommendation systems. So, the basic assumption in recommendation system is that people will like stuff, things similar to other things that they like, okay, or things that that are liked by people with a similar taste. Okay, this picture shows that okay, the biker and another athlete, they are similar, okay, and they have purchased similar stuff, okay, like food, salad, and this athlete on the right, he purchased Coke or some drink, soft drink. So then, because these two persons, the biker and the athlete, are similar, so then we would like to recommend the soft drink to the biker too. Okay, so a classic example is the Netflix problem. So about 10 to 15 years ago, Netflix, which is a company renting movies, they have posed a challenging. So they have many movies or to rent, and they also have many users. So the users usually don't provide ratings, and if they do, they don't provide ratings to all the movies that they have watched. So Netflix would like to complete these ratings so that they can recommend movies to users. So the challenge that they imposed at that time has 0.5 million users for 17,000, more than 17,000 movies. So they want to predict user ratings so that they can recommend movies. As you can see from this picture, the question mark, that means there's no rating, okay? So we can formulate this problem in a more mathematical way. So we are given a partially observed noise matrix, and we would like to approximately complete it. In Netflix problem, MUI means the rating on movie I by user U. And we need to estimate those unrated movies, okay? So as we know, we can always express the the variance of the data by a low rank matrix. So a few factors, a small number of factors can explain the most of the variability of the data. So basically, I'm saying that this matrix can be represented as the product of low rank matrices. Okay, so in this way, hopefully, if we can find this low rank matrix, we can recover or predict the unrated movies. So the problem can be formulated as a problem like this. So we use A to denote the index set of the given weight ratings. And then we would like to minimize the difference between X, which is the matrix we want to recover, between X and M. M are the rating that have been given, subject to the matrix, subject to the constraint that the nuclear long of the variable capital X to be small, okay? So the nuclear long is defined as the summation of the singular values of the matrix, okay? So again, the problem is challenging for the following reasons. Firstly, it is of high dimension. As you can see, the matrix X are 5 times 10 to 6 rows and 17 times 10 to 3 columns. And also, we would like to have a sparse solution. A sparse solution means we only have a small number of non-zero singular values. That means the rank of the matrix is small. And also, we don't need to have very highly accurate solution. One more thing about this matrix completion is that usually we cannot afford to do full singular value decomposition because the matrix is so large. Okay. So I will talk about one more example. The first two examples are popular, and both of them arise from data analysis or statistics. The last example, I think is very interesting. It is arise from health industry. So you will see the sparsity and high dimension, all of them have some physical meaning. So so this is arising from the intensity modulated radiation therapy. So every year, 1.7 millions of people are diagnosed with cancer. Okay, IMRT is an effective approach that those patients can possibly benefit from. Okay, so in IMRT, the patient irradiated by linear accelerator from a few different angles. As you can see from the picture on the right, so there are 3 different angles that can possibly provide radiation to the patient. And then the structure of the patient are discretized into small voxels. So the patient has many structures, and each structure is discretized into small voxels. Okay, so then okay, from each angle, the radiation are organized into the so-called apertures. Okay, basically a beam from each angle is decomposed into a rectangular grid of beamness. Okay, so as you can see the picture from the bottom, so you have a rectangular area where the beam can be applied. Okay, so if a beamnet is not blocked by either the left leaf or the right leaf on each row of the rectangle, then this beamnet is going to be effective. Okay, this beamnet will be applied to the patient since it's not blocked. Okay, so the aperture is defined as the connection of the effective beamness. Okay, as you can see, the motion of the leaves in each row controls the set of effective beamness and hence the shape of the aperture. Okay, so the doctors will apply a series of use a series of apertures to apply the irrigation so that they can treat the patient. Okay, so if we use Ka denote the set of allowed apertures, okay, so then the rectangular grid in each angle has m rows and n columns. So then the total number of possible apertures in each angle will increase exponentially with respect to the number of rows in each angle, okay? So then, as we said, the shape of the aperture is described by these binary variables, x,k,a. So x,k,a equal to 1 if the beamnet ij is effective, and 0 is not effective, okay? So the decision we also need to make is to determine the influence rate from each aperture. So this will be used to determine the dose intensity and the amount of radiation time from each aperture, K, okay? So the problem can be formulated as an optimization problem in the following way. So as we can see, the dose received by a Voxel from a beamnet is denoted by by ZV, which basically is a summation of all the doses received from all the apertures, okay? And then the object function is defined as, basically a penalty function that requires the dose received in each voxel be within a certain interval, like under 90 and over 90, okay? So this object function acts as a surrogate for some clinical criterion that we are going to talk about a little bit later. So then the basic formulation for IMRT treatment planning problem is to minimize this quadratic or penalty function subject to this simplex constraint. So basically, I'm saying that the summation for all the intensity from each angle will be less than to 1. And then I want to minimize this penalty function, okay? So the challenging of this problem is as follows. Firstly, the problem is of huge scale. So the size of y can exponentially increase with respect to m, as we said. So if the rectangle is 10 by 10, and if we have 180 angles, like basically every 2 degrees we define the angle, then the dimension for the problem is 180 times 45 to the power of 10, okay? So it's of huge scale, and existing solution methods cannot handle this problem efficiently. Sparsity, usually, okay, we want to have a small number of apertures and a small number of angles. A small number of apertures and or a small number of angle imply a small amount of radiation exposure to the patients. Also, we don't need to solve this problem very accurately because, as we said, the object function f acts as some surrogate for some clinical criteria. Okay, so all these problems appear to be very challenging. It turned out, we can use a very simple algorithm, a conditional gradient method, to address some of these challenges. So conditional gradient method is one of the earliest method or first order method initially developed by Frank-Wolfe for solving a simple convex optimization problem. You minimize the convex function f over a convex compact set. Okay, in the basic setting, we assume that f is smooth. That means f is differentiable and the gradients are Lipschitz continuous. Okay. So in conditional gradient method, we assume that we can solve a linear optimization problem over the set capital X. So that means for any given P, we can compute a solution of minimizing P times X over the set capital X. Then once you have this, the algorithm is very simple. The algorithm just had 3 lines, right? In each iteration, we first compute the gradient at the search point xt, and then we minimize the linear approximation of the objective function over the set capital X, and then we do a convex compilation between the previous search point xt and the current solution yt for the linear optimization problem. Okay, so this algorithm does not require us to do projection. So all we need is to do linear optimization over the set. And also the only parameter for this algorithm is alpha t. And a classic way to specify alpha t is to set it to 2 over t plus 1, okay? And alpha t can be improved if you do a simple line search procedure. So then, as you can see from this picture, this algorithm is different from projected gradient. I gave a very simple example as an illustration. So I want to minimize x squared plus y squared, subject to x plus y equal to 1 and xy non-negative. So the optimal solution is given by 1/2 and 1/2, okay? The left picture shows you how the projected gradient goes for this particular problem. So I start with the point 0, 1. So you move along the gradient direction, and then it will be outside the feasible region. Then you do projection over the feasible region, so you get to a new point. And for this problem, at this new point, you do move along the gradient direction, and then project back to the feasible region. So you do this again, and then you will finally converge to the optimal solution. Okay. So conditional gradient is a little different. So I'm actually starting from 1 and 0. Of course, you can also start from 0 and 1. So I start from 1, 0, and then I start from this point. I do a linear optimization that gave me a solution, actually extreme point 0, 1, and then I take a convex compilation between this this solution 0, 1 and my current solution 1, 0. Then I'm going to move to this search point here. That is a convex compilation of these 2 points. And then at this point, I'm going to do a linear optimization that gives me a exponent solution 1, 0. Then I'm going to take a convex compilation between this point and the extreme point 1, 0. Then I'm varying at this point. Okay. As you can see, for conditional gradient, I'm going to swing back and forth around this optimal solution. Okay. So conditional gradient is simple. We don't need to choose step size. It's projection free. So we only need to solve a linear optimization problem. So it is useful, especially if the projection step is complicated. It also gave us sparse solution. As we can see, at every iteration, we just add a new extreme point. Okay, so we think if the constraint is simplex, so then each extreme point you just have 1 non-zero. So the number of non-zero that you're going to have in the solution will be less than or equal to the total number of iterations you have. Okay, so but the convergence of this algorithm. Okay, so so the algorithm is simple, does not require projection, and gave us a sparse solution. But the convergence is lower than other algorithms like project gradient or accelerated project gradient. So basically, if you want to get accurate solution with accuracy epsilon, approximate solution with accuracy epsilon, then the number of iterations we need is order of 1 epsilon. Okay. So the number of calls to the linear optimization oracle is not improved. Basically, this 1 over epsilon is not improvable, but the number of gradient computation can be improved. Okay. And there are also some other work extending this algorithm for solving non-smooth problems or non-convex problems. But now let us see how we are going to apply this method for solving the motivating problems that we discussed before, okay? So if we want to apply this algorithm for novelty detection, we call that we are going to solve a quadratic optimization problem over a simplex constraint. Then the only thing that we need to do more carefully is the linear optimization, right? But this step is also easy. Basically, we just need to choose the most negative gradient component and then return the corresponding extreme point, okay? As we said, even though the problem is a high dimension, but the complexity guarantees is almost independent of dimension. And also the, as we said, the number of non-zero elements will also be bounded by 1 epsilon. So we can guarantee to have a sparse solution. Because we don't need to solve the problem to high accuracy. So we don't need epsilon to be too big. So this low convergence of the algorithm is acceptable, okay? And also the algorithm is simple to implement. So now let's see how we are going to apply it to matrix completion. So again, what we need to do more carefully is how to solve the linear optimization problem, right? So this is easy because all we need to do is to find the largest singular eigenvalue, largest singular value of the gradient, okay? So once we find the largest singular value and the corresponding singular vectors, then we can solve this linear optimization problem by returning, you know, this R times UT and the VT transpose, okay? So for this problem, the complexity is independent of dimension. Again, the sparsity is guaranteed because the rank of the solution is bounded by 1 epsilon. And is acceptable because we don't need to seek accurate solution. And if we want to implement this algorithm, one nice thing is we don't need to do full singular value decomposition. We only need to do the largest singular value decomposition. Okay, so how about we apply this problem to IMRT? As we said, in IMRT, the dimension of the problem is exponentially increasing. So we can basically we cannot apply a gradient projection method because we don't even want to compute the full gradient because the full gradient is 45 to the power of 10. So there's no way for us to compute it. So if we want to apply conditional gradient, what do we do? Okay. If we apply conditional gradient to IMRT, we want to do gradient computation and linear optimization simultaneously. Okay. So for a given y, we first compute the gradient with respect to z. Okay. And then as we will see, in order to find the most negative gradient component, means that we want to find the most negative, the aperture with the most negative gradient component. What we do is to examine the rectangle grade in each angle, row by row, and we select the position of the leaves, resulting in the smallest gradient along this row. And then in that way, we are going to fix the binary variables xij for the selected aperture. Okay, so in this way, we are going to do gradient computation and linear optimization simultaneously. We don't need to compute the full gradient information. Okay, so this algorithm can be implemented efficiently, even though the number of decision variables is 45 to the power of 10 or something like that. The number of apertures that we are going to have will be bounded by order 1 epsilon. So even though the potential number of apertures is huge, but the solution that we obtain is bounded by 1 epsilon. Okay, so that can be used to address this huge dimension problem in IMRT. Okay, so then what are the remaining challenges that we can see? Okay, so with a very simple algorithm, it seems that we address most of the challenges that we point out in the beginning. Okay, but the limitation of conditional gradient is at least one of the limitations is that this algorithm only handles very simple models, okay? So it requires the linear normalization over a simple convex compact set, okay? For example, in the matrix completion problem, if we add some simple linear constraint, okay, we'll make the sub-problem as hard as a general semi-definite program, okay? For IMRT, for this type of problems, we often have different function constraints, okay? One is to use group sparsity constraint to ensure that we have a small number of angles, okay? And another important constraint is risk-averse constraint used to avoid overdose or underdose for either normal or tumor structures, okay? So existing conditional gradient method cannot be used to solve problems with this type of constraint, either linear or function constraint. So that inspires us to develop some new projection-free methods for solving problems with general function constraints, okay? So this part we are going to talk about briefly some of our recent research results, okay? So in this problem, this is actually a very classical convex optimization problem. We minimize f subject to linear constraint gx defined as ax minus b equal to 0. And we have convex inequality constraint hix less than equal to 0. So capital X is a convex compact set. And we can only do linear optimization over the feasible region X, and we don't want to do projection. So f at h are a proper loss and continuous convex function is linear mapping. For simplicity, we also denote hx as a set of these functions hi. Okay. So since we don't want to do projection over the feasible region, so naturally we can consider is Lagrangian relaxation or side point reformulation. So now basically we say, okay, we have this side point problem, want to minimize with respect to x, maximize with respect to y and z, which are dual variables. Then you may think about, okay, we may apply smoothing technique next of developed to solve this problem. But indeed, this has been done. But this smoothing conditional gradient method is not applicable in our setting because it cannot deal with the linear coupling term, the nonlinear coupling term, hx times z. It can only deal with the linear coupling term gx times y. And also it cannot handle the unbounded dual feasible set. So recently we have developed a constraint extrapolation method. It can achieve the optimal complexity for solving a wide range of function constraint problems, but this method also requires projection over the feasible region capital X. Okay, so basically we don't have efficient projection-free method for solving this function constraint or convex optimization problems. Okay, so we decide to develop a new algorithm called Constraint-extrapolated conditional gradient method. So as you can see, this is a single loop algorithm. In each iteration, we are going to do a few steps, this step, and then we do a linear optimization over the feasible set, okay? So even though the S algorithm looks more complicated than conditional gradient, but as you can see, the crucial step is to do linear optimization to define PK, okay? Before we define PK, the first two steps is called constraint extrapolation. Basically, these are just vector summations, or is easy to compute. And the next two steps are dual ascent step. So basically, we update dual variables. These are also easy to perform. And then we do linear optimization. The last step is convex compilation, similar to conditional gradient method, okay? So is there any question about this algorithm? Okay, so then, so how it converges? So if we choose the parameters alpha k, similarly to 2 divided by k plus 1, lambda k, which defines the extrapolation, is k minus 1 over k, and tau k basically defines the dual ascent step size. Here, I require that the number of iterations capital N is given to me in advance, okay? So my algorithmic parameter setting relies on the total number of iterations capital N, okay? Using this parameter setting, I can show that I will be able to find a solution so that fx bar minus fx star, x star is open solution less than equal to epsilon, and the constraint violation gx bar, which corresponds to the linear constraint, and the hx bar for nonlinear constraint. The violation of this constraint are smaller than epsilon in at most 1 epsilon square iterations, okay? So we show that this algorithm will converge, and we bound the total number of iterations required for convergence. And also we mentioned that this 1 epsilon square appears to be tight. What is interesting is that even though the basic result we require both f and hi are smooth convex functions, but even if your function f and hi are not smooth, but they allow a smooth approximation, okay, then a similar order 1 epsilon square can still be obtained, okay? This was a little bit surprising to us because usually we think if you apply smoothing technique, the convergence will be slowed down. But for this particular function constraint problem, the convergence will be the same as for smooth problems, okay? One potential shortcoming for this algorithm is that we need to fix the number of iterations capital N a priori, okay? So in order to address this, we show that we can improve it by removing this assumption, okay? So to do that, we develop a variant called Constraint-extrapolated and Dual-regularized conditional gradients. The idea is like we are going to add a diminishing regularizer for the dual ascent steps, okay? The diminishing regularization is called gamma k over 2 y minus q0 square, okay? Similarly for the inequality constraint part, okay? So we are going to choose gamma k so that it goes to 0. So as you can see from the below, this line below, we are going to choose alpha k 2 over k plus 1 and lambda k as before, and tau k square root of k, and gamma k now does not depend, both tau k does not depend on the total number of iterations, capital N. And the gamma k is chosen in a weird way, but it goes to 0, okay, it's diminishing. So in this way, we can show that this CoexDurCG achieves similar convergence as CoexCG. And we don't need to fix capital N in advance, but the analysis is a little bit more involved than the basic version of CoexCG. Okay, so then we decide to now apply these algorithms to IMRT problem. Okay, so we introduced a basic formulation of IMRT before, but in application, in reality, we need to have more constraints. So the clinical criterion for IMRT is usually stated as a violated risk constraint. For example, this PTV 56 and V56 greater than to 95% means the percentage of voxels in the structure PTV56 that receives at least 56 gray should be at least 95%. Okay, and similarly for those healthy organ or healthy structure like PTV68, we are saying that the percentage of voxels in this healthy structure PTV68 that receive more than 74.8 gray should be at most 10%. Okay, so these are valid risk constraints, and in our formulation we use conditional weighted risk as an approximation. So basically we say that we can approximate it closely by using a convex function. Okay, and there are also some other function constraint called group sparsity. In the basic formulation, the simplex constraint can only guarantee that a small number of apertures, but in practice, a small number of angles is desirable because we don't necessarily rotate around the patient often. That will reduce the treatment time and radiation exposure significantly. So we decide to incorporate a group sparsity constraint defined as like the summation of the maximum of yk or yk smaller than or equal to a threshold phi. So intuitively, this constraint will encourage the selection of apertures in those angles that have already contained some non-zero elements of y. Okay, so in this way, we are going to encourage a small number of angles in the final treatment plan. In the end, we have this. So we still want to minimize this quadratic penalty, and we have under those constraint, over those constraint, group sparsity constraint, simplex constraint, and some non-negativity constraint and a box constraint. Okay, so in this problem, we have smooth objective function, and we have a structure non-smooth constraint, and we have simplex plus box constraint. So we can apply the algorithms that we developed for solving this problem. Okay, so as we said, the complexity, the number of iterations that we require to solve this problem will be bounded by order 1 epsilon square, and we can design a similar procedure as before to simultaneously solve the linear optimization problem and compute the most negative combined gradients of the objective function constraints. Okay, so we don't need to compute a full gradient, and we don't need to do projection. Okay, for both. For solving this problem, in order to test the algorithm, we applied both randomly generated instances and also some real data set. Okay, our goal is to compare the CoexCG that require us to fix the number of iteration and CoexDurCG that is more adaptive. Okay, and also we want to study the sparsity constraint. We want to see whether incorporating this group sparsity constraint will give us a solution with a smaller number of angles. Okay, and of course we want to meet the clinical criterion, because to meet the clinical criteria are the most important. Otherwise, this treatment plan cannot be applied to the patients. Okay. So we generate firstly some random instances. As you know, because of the privacy issue, the real data set for from the for the patients are very limited. Okay. So in order to compare our algorithms, we decided to randomly generate some instances. So these instances are not very big, in comparison with the real data set. Okay, but it is sufficient for us to compare different algorithms. Okay, so so here we compare the two variants, CoexCG and CoexDurCG, and our conclusions are that these two algorithms are comparable in terms of the solution quality, like the constraint violation and the objective value, as well as the CPU time. Okay, but the CoexDurCG is more convenient for implementation because it does not require us to fix the total number of iterations capital N in advance, okay? And then we also applied our algorithm, the CoexDurCG, to the real data set is for a prostate cancer data. So as you can see, the data set for this problem is quite big. The dimension is 2 × 10⁻30. So we have this this number of potential apertures. Okay, the number of voxels is reasonably okay. Okay, but you still have 3 million. So we have 10 clinical criterion. So the whole goal is to satisfy these 10 clinical criterion. Okay, either underdose or overdose constraint. Okay, so we showed that our results satisfy all these criterions. Moreover, by playing with that group sparsity constraint, try to change or modifying the right-hand side phi, we can reduce the number of angles from 39 to 3 without sacrificing much of this clinical criterion. So basically we're saying that now you don't need to rotate around the patient many times, just 3 angles will be enough to treat the patient. Okay, so these are some those works histogram that people are using in healthcare industry to show how these the clinical criteria are satisfied with respect to different number of apertures. Okay, now here we compare if we use 39 and or use just 3 angles. Okay, from in the left you have 39 angle, right you have 3 angle. As you can see, the clinical criterion does not change it too much. Okay, they will be satisfied. Okay, of course this is just for one criterion, and we in our paper we show that all the criterions will be satisfied. Okay, so I think this is a brief summary for what I talked about. So I gave a brief introduction about the conditional gradient methods. Okay, conditional gradient methods over simple sets, they can handle high dimensionality and generate sparse solutions. They are most appropriate if you don't need to solve this problem very accurately. Okay, and our new algorithm CoexCG and CoexDurCG significantly extend this method for solving problems with affine, smooth or non-smooth function constraints. As we mentioned, these type of methods can be used for solving a wide range of applications, like novelty detection recommendation systems, IMRT. It can also be applied for solving like structured support vector machine problems. It may also have the potential to solve a more general classical convex optimization problems like semi-definite programming problem. Okay, I think that's all what I want to talk. Thank you very much for listening to my talk. And here are a few references that you may find helpful. Okay. I would like to take any questions here.
Thank you very much for your talk. It was great. And now we can start questions.
Hi, Yanhu. This is Anatoly speaking.
Yeah, Anatoly, nice.
Thank you very much for a nice talk. I was just thinking, if instead of applying your method, extrapolated method, if instead of this, we try to act as follows. So we build min-max problems. We consider a sequence of min-max problems. And then we solve the dual problem because the linear minimization oracle for the primal will supply the subgradient observation for the dual. The dual is simple because it's only simplex, so we can just use the subgradient descent for solving the dual. Then we use the certificate to rebuild the primal solution. Okay.
Yeah, but there is a possibility.
And then we would just use Newton or bisection to find actually the solution of the constraint problem through the sequence of min-max problems. All right.
Yeah.
as far as I understand, of course the algorithm is more complicated because you have stages, you know, and but the final accuracy estimate will be essentially the same because Newton will converge linearly, and you just, if you adjust the accuracy at different stages, you know, you don't need to solve to epsilon accuracy starting from the beginning in initial stages. You don't need high accuracy. Then basically I think it should be like 1 over epsilon square also.
Yes. So I think that's another possibility, right? So you basically switch the prime and dual and using subgradient descent to solve the dual, right? And then you recover the primal solution.
Okay. Yes.
Yeah.
But, okay. Of course, your algorithm is easier because you recover directly the primal solution, and you don't have the stages and adjusting parameters and so on. So it looks much easier indeed.
Yeah.
Okay. Thank you, Yang-Hu.
Thank you for the question.
Thank you. Any question else?
Hello, George. I also have one question. So it's about number of constraints. So does it make sense to use, for example, in the main update rule, to use some subset of constraints in order, in case if it's computationally hard to use all of them? Does it make sense, or it's not applicable?
Yeah. So if I understand, that means if you have a very large number of constraints, can you use a small number of constraints to every iteration, right?
Yeah. So what are the guarantees?
Yeah, so that's an interesting problem. We have not started that yet. But I think it might be interesting direction to explore. So maybe you use some randomizing, incorporating some randomization scheme into this algorithm. Basically, you're saying that when we update the dual variables, I don't want to update all of them. Yeah. But yeah, I think that's if indeed there is large number of constraints, that might be a good idea to explore.
Okay, and so
also there is a question in chat.
Yeah.
Can you see it? Or
okay,
I will.
Let me see.
Is there any modification of the algorithm CoexCG for saddle point problems with function constraints? Similar to Frank-Wolfe algorithm for saddle point problems by authors.
Okay, I don't think so. As I said, so this is something new, right? So we just released the paper like within 1 month. So there's no such extension yet. But I think all these questions are interesting. Will be interesting to explore. So basically, if you have a min-max problem and you have a function constraint, how are you going to solve it? Right? I think that seems to be an interesting problem to study.
Okay, thank you. George, I also have a question about your estimate 1 over epsilon square. You say that this bound is tight. Could you clarify why this bound is tight? Because we have an intuition that for smooth problem, conditional gradient algorithm converge like 1 over epsilon, but this is on a simple convex set, and you have constraint. So maybe it is because of constraint, but what is maybe a deeper reason? Maybe
so
you can explain it.
Yeah, I can explain a little bit. It's not exactly the same setting, but so if you minimize a bilinear side point, like your min max ax times min with respect to x, max minus with respect to y, and you minimize min max ax times y. Okay, this bilinear side point problem. There is a worst case example showing that if you don't do projection over x, then the number of linear optimization will be at least 1 over m squared for solving that problem. So it's indeed it follows from the constraints or the non-smoothness of the problem. So I don't know if I answer your question very clearly.
Oh yeah, I see. Okay, thank you.
Yeah.
So, okay, if there are no questions, so let's thanks speaker one more time. This was a very interesting talk and based on very recent work. George, thank you very much. It was very nice.
Thank you.
And next talk will be on September because we have holidays. This is we spent at serious student school during August, so that is why we decided to stop seminar until September. So thank you one more time, and see you in September.
Thank you, everyone. Thank you for coming to my talk.
Thank you, George. Thank you.
Bye.
Thank you very much.
Thank you a lot.